Happy 4th of July. Happy birthday to the United States. 249 years old. Right, Scott?
Yeah. Yeah. Pretty amazing. Next year, 250.
And
That is
we'll
so,
be
that is going to
live
be
for the 250th birthday. We'll be there.
Well, we hope so. Yep. Planning on it.
Yeah, I hope so too. It's like milestone, like the 100th birthday, the 250th, a quarter century.
And our country will be run by a government that is intact cognitively. So we like that.
Yes, definitely. Oh, I'm Steve.
And I'm Scott.
And together we are Backyard Musings. Thank you for joining us.
Yep. And we are talking science and technology, a little quantum stuff today.
Yes, sir. This is really cool. Researchers at the University of Rochester and Rochester Institute of Technology have recently linked their campuses using an experimental quantum communications network built with 2 optical fibers. We've been talking about this, that the quantum, they communicate by optical fiber. And if you think about it, like Frontier, Roadrunner, all your big communications where you watch TV, they're all fiber too. So pretty soon we'll be dialed in with quantum computers. In a new paper published in Optica Quantum on April 24, 2025, the team introduces the Rochester Quantum Network, RoQNET, which transmits information using single photons, which is a qubit, over approximately 11 miles of fiber optic cable at room temperature and optical wavelengths. Would you like to know more?
Quantum communications networks could greatly enhance the security of transmitted information by making it possible to copy or intercept messages without detection. Interesting. These systems rely on quantum bits or qubits, which can be made from atoms, superconductors, or even imperfections in material like diamond. Okay. Among these photons, individual light particles are the most suitable qubit for long-distance quantum communication.
Light particles, speed of light. Talk about hyper fast. Oh my gosh, right?
Yeah.
Photons are especially attractive for quantum communication because they can, in theory, travel through the fiber optic telecommunication lines that already span the globe. In the future, a variety of qubit types will likely be used since sources like quantum dots or trapped ions offer specific benefits for applications in quantum computing and sensing. Didn't we, the other day, we talked about how they achieved 95% coherency for quantum computing with only 5%, missing the mark? I think we did that a couple of days ago, Scott.
We have talked about quantum stuff a lot. So
yeah,
probably did.
Even so, photons remain the most compatible with current communication infrastructure. That's the key. You don't have to build new infrastructure. The new paper focuses on enabling quantum communication between different types of qubits within a network.
Quote, this is an exciting step creating quantum networks that would protect communications and empower new approaches to distributed computing and imaging, says Nicholas Vamavakis. The Marie C. Wilson and Joseph C. Wilson Professor of Optical Physics, who led the University of Rochester's efforts. Go on with a quote, while other groups have developed in experimental quantum networks, RoQNET or RoQNET is unique in its use of integrated quantum photonic chips for quantum light generation and solid-state based quantum memory nodes.
Folks, you heard it here first. We're calling this the quantum net of things. Quantum net.
Okay.
You heard it here. All right. The teams at the University of Rochester and RIT combine their expertise in optics, quantum information, and photonics to develop technology with photonic integrated circuits that could facilitate the quantum network. Currently, efforts to leverage fiber optic lines for quantum communication require bulky and expensive superconducting nanowire single photon detectors, which we'll get into that later at the end of the segment. But they hope to eliminate this barrier.
Quote again, photons move at the speed of light and their wide range of wavelengths enable communication with different types of qubits, says Stefan Prebel, a professor in the Kate Gleason College of Engineering at RIT. I don't know where RIT is. Maybe Rochester Institute of Technology.
Yeah.
Okay. Go on with a quote. Our focus is on distributed quantum entanglement, and RoQNET is a test bed for doing that. Ultimately, the researchers want to connect RoQNET to research facilities across New York State at Brookhaven National Lab, Stony Brook University, Air Force Research Laboratory, and NYU, New York University.
Yeah, cool. So this looks like regional nodes. Awesome.
Yeah.
This will pop up into a quantum net. Really awesome. Okay, here we get into the technical stuff. The superconducting nanowire single photon detector is a highly sensitive device used for detecting single photons in the optical and near infrared spectrum. Remember that, optical and near infrared. They are the highest performing detectors for this purpose. We explain it using 4 advantages. We'll alternate on these, Scott. You go first.
Functionality. SNSPDs operate by utilizing a current-biased superconducting nanowire, which becomes resistive when a photon is absorbed, allowing for the detection of single photons with high timing, precision, and recovery times.
Okay.
You want me to do that one too, or is that?
No, I'll do this one. You do the next. We just alternate.
Got it.
Applications. They are employed in various fields, including quantum optics, quantum communication, and imaging due to their superior performance compared to traditional single photon detectors.
Design. The detectors are typically designed in a meandered geometry to maximize detection efficiency over a 2-dimensional plane.
Yeah, I can't wrap my head around that. I mean, it's going to meander, you know.
Oh, come on, man! I do this stuff all day. I'm the meander geometry. I do that every day. I mean, that's what I do to exercise my brain.
Okay, the last one, technological advancements. Ongoing research aims to enhance their capabilities for photon counting, fast time tagging imaging, and integration with quantum photonic circuits. So I guess those little ends are where they communicate. If we can mass produce those ends and put them at the fiber optic nodes, then we can just quantum all around.
Sounds like a side hustle.
Yeah, it could be. Like one of those RJ45 jacks that you put at the end of the Cat 5 wire.
Yeah,
that's exactly what this is. I mean, very similar. I mean, but different.
Because they're going to use it. You said they're going to use the same cable, right?
Yeah, same fiber optic. They just got to put these little jacks in at the end, for lack of better words, so they can connect.
I wonder if you could use a different. So they're still going to use the same jack that's on the Cat 5? No, they're going to have to put a new jack on or an adapter.
It's these detectors. I'm just calling them jacks, for just to wrap my mind around it. Okay. But to me, that would be the weakest point in the link that you could exploit, because they say you can't break in. At those detectors where they connect, that's where you can hijack. That's what I would think.
Got it. Yeah. Okay. Good story.
All right, folks, we're going to catch you in the afternoon when you're barbecuing your burgers.
Yeah, when we're all about mice in the laboratory, we're all about quantum. We like the quantum. Take care, everyone. Thanks.